Thank you very much for this invitation, which can look a little strange, given that I'm a member of the scientific committee. In fact, this talk should have been given by Marıa Angelica Cueto, who is a friend and collaborator, and she could not come, and I accepted, asked by the other members of the scientific committee to replace her. And in fact, I will speak about things we learned during a long-term collaboration, which is still ongoing, and a collaboration which started here in CIRM during a work in triples some 10 years ago. So I want to thank them, Angelica Cueto and Dmitry Stepanov, for everything we understood and we did together. Till now, we published these two papers, the Milnor fiber conjecture of Neumann and Wahl and an overview of its proof in a kind of Bible, some 1,000 pages volume in honor of Norbert Campo, and the local tropicalizations of splice-type surface singularities. And a lot of things I will present come from these two papers. But my talk will be partly mathematical and partly historical. I want to present you extracts from foundational papers. So this would have been impossible to do at the blackboard. So that's why I prepared a beamer. So my talk is difficult to note. So what I ask you, please, just note when you don't understand something, when you have remarks, if there are errors. I would like to improve this beamer. At the end of my mini course, it will be available for everybody interested. So I would like to still improve it in this way. So please note that everything which appears in magenta, like here, is clickable in the beamer. So if you click, you access directly to that paper. So you can immediately go and spot what I showed in the biggest contest. So our initial motivation when we started working together was a conjecture formulated in a 2005 paper by Walter Neumann and Jonathan Wahl, which is a Milnor fiber conjecture. This conjecture is visible here. So let's see. It tells that something, which is called F, is homeomorphic to the result of pasting. So we are in topology, the realm of cutting and pasting, the main obsessions of topologists. And what we have to paste here is something called F10, something called F20, and there is an intermediate object here, which is a Cartesian product of G1 and G2. And here, when we make unions, it tells along what to paste. And the way to paste is written here. But for me, an image is worth 1,000 words, so I will explain you this using an image. So you see here, in fact, the objects we are speaking about are four-dimensional manifolds, so it's difficult to represent them. So these are symbolical images. What we have are FA and FB here, which are four manifolds with boundary. And inside each one of them, there is a properly embedded surface. So when I say surface, it means a real surface with boundary. The boundary is made of a finite collection of circles. Properly embedded is exactly like here. It means that no part of the boundary lies in the interior of the manifold. The boundary of the surface lies completely in the boundary of the big manifold, and there, at the level of the boundary, one has transversality. So what one does, first one cuts along GA and GB. So the result of cutting along GA, you see it here. This calligraphic C indicates a cut. So you create here a place. Here you cut along this and you create a place. And precisely in this place, one can glue a Cartesian product of GA and GB. So the operation defined by Neumann and Wahl, which is called a splicing procedure, uses this central piece here, which is this Cartesian product. And what they say precisely is written here. Their conjecture states that the Milnor fiber of a special type of surface singularity, which is called a splice-type singularity, is obtained by splicing the Milnor fibers of two simpler such singularities. So we are playing a game inside a specific class of singularities, and what they said that inside this class, in fact, everything can be decomposed into very elementary pieces. And the basic operation, which is like taking a molecule and cutting it inside in two simpler molecules, it has this topological description. So what I will tell in this mini course is successively what follows. First of all, I will present the prototypical decomposition occurring in singularity theory, the plumbing decomposition of the link of a complex normal surface singularity, obtained once a normal crossings resolution of X is fixed. This was the model from which then ramification occurred and more sophisticated decompositions were produced. In particular, starting from their model, were obtained decompositions of Milnor fibers. So I will speak about an analogous decomposition of the Milnor fibers of a function, but again, once a normal crossings resolution of the function is fixed. Then I will explain how logarithmic geometry in the sense of Fontaine and Illuzy may be used to decompose canonically the Milnor fibers using an operation called rounding introduced by Kato and Nakayama. So here, in fact, I will speak about the properties of log geometry. In this first approach, which can look non-standard because I won't start with the definitions, I will look globally at logarithmic geometry and I will explain what good properties we find inside it which help us decompose Milnor fibers, in the hope that I will give you the desire to know the definitions. Because understanding a definition is not only a problem of logic, it's also a problem of desire. And how to make desire appear is a big problem, is part of the art of a person who explains. Then I will present several viewpoints on local tropicalization and how it leads to toroidal resolutions in the Newton non-degenerate cases. So you saw in the previous parts, I specified each time that one had normal crossings resolutions. And that's where local tropicalization appears. It helps getting resolutions, but we will see that we do not get directly to normal crossings resolutions, but to something more general, toroidal resolutions. And we will see that combined with log geometry, this works very well. Then only I will define splice-type singularities. So this could be strange. If I say that our motivation was something about them, why don't I define them first? Because it will be enough to tell you a basic property of splice-type singularities which motivates the rest. And when we will enter in our proof, there finally the precise definition will be useful. So after defining them, I will present the principles of our proof of the Milnor fiber conjecture. And finally, I will arrive at the moment when I will give the precise definitions of log geometry and the rounding of complex log structures. And I hope that you will not suffer from this non-standard viewpoint. So let's start with the prototypical decomposition, that of the link of a complex normal surface singularity. It was introduced by David Mumford in one of his first papers, published in 1961, the topology of normal singularities of an algebraic surface and a criterion for simplicity. Let's read the first lines. Let a variety be embedded in complex projective space of dimension m. And let P be a point of the variety. About P, choose a ball U of small radius epsilon in some affine metric. So we see a standard metric, Euclidean metric here. Let B be its boundary, and M be the intersection of the boundary of the ball with the variety. Then M is a real complex of dimension 2n minus 1, and a manifold if P is an isolated singularity. Complex means, say, simplicial or cell complex in the sense of algebraic topology. Why? Because if you don't assume that P is an isolated singularity, then the singular locus gets out of the point, and when you intersect with a ball, you will get singularities in that intersection. So in general, it's not a manifold. That's why he speaks about a complex at this point. The topology of M, together with its embedding in the sphere, reflects the nature of the point P. So this is a basic object of study in this paper, this intersection, which came to be known as the link of the singularity. And what's his motivation for studying this object? Well, from the standpoint of the theory of algebraic surfaces, the really interesting case is that of a singular point on a normal algebraic surface, and M arbitrary. Normal implies isolated singularity. So in this case, the link M will be a three-manifold, a closed, connected, oriented three-manifold. M is then by no means generally S3, and consequently, its own topology reflects the singularity P. So why does he say it is not generally S3? Because just before he explains that for curves, when you have any branch of a curve, you get a circle. So for curves, even if you have a singularity, the link does not see it. But by contrast, the topology begins to feel the singularity when you are in the realm of complex surfaces. In this paper, we shall consider this case first giving a partial construction of the fundamental group of the link in terms of a resolution of the singular point P. Secondly, we shall sketch the connection between the homology group of the link and the algebraic nature of P. Finally and principally, and this was the starting point of his investigations, we shall demonstrate the following theorem conjectured by Abyankar. Theorem: the fundamental group of the link is trivial if and only if P is a simple point of F, a locally normal surface. And F, topologically a manifold at P, implies that the fundamental group is trivial. So in fact, if you have pi1 trivial, then you have a smooth point, therefore the link is S3. So in particular, this shows that singularity theory in this way could not produce a counterexample to the Poincaré conjecture. So let's see now how he attacked this problem. We have in mind that we want to compute the fundamental group. And at that moment, it was clear that computing a fundamental group of a space amounted to decompose the space into subspaces. Because a prototype of computation of fundamental groups was Van Kampen's theorem, which Van Kampen had proved answering a question of Zariski, who was the thesis advisor of Mumford. So we feel here that we are in a genealogy of problems. It's the same family, people looking at related problems. So, how to arrive at pi1? First, resolve. A normal point P in F is given. A finite sequence of quadratic transformations, which means blow-ups, plus normalizations, leads to a non-singular surface F prime dominating F. This is one of the methods of resolving the singularity, which was proved by Zariski at the beginning of the 40s, that if you repeat these operations, you can resolve singularities of surfaces. But Mumford does not use this precise procedure. This is a prototype of paper which uses existence of resolution of singularities, but not the precise method. The inverse image of P on F prime, which is called nowadays exceptional divisor, is a union of a finite set of curves, E1 to En. By further quadratic transformations, if necessary, we may assume that all EI are non-singular, and different EIs, when they intersect normally in exactly one point. This is what is called nowadays to have a simple normal crossings divisor. And this point, precision, does not lie on any other EK. So it means that their union has smooth components, and what we see locally is only two smooth branches intersecting transversely. This will be a great technical convenience for everything he does in his paper. But now he wants to study the link. The idea is that the link is a level of the functions, the sum of squares of absolute values of the coordinates in the ambient space. Now this function can be lifted to the resolution, and one can look at those levels when one gets nearer and nearer the exceptional divisor. So this is what he says here. Now notice that M may be also defined as the level manifolds of the function P square on the non-singular surface F prime. It is as a tubular neighborhood of the exceptional divisor that we wish to discuss M. So please notice that what he calls tubular neighborhood is what topologists call boundary of tubular neighborhood. Okay? But we will play with both things at the same time. We are interested in tubular neighborhoods as compact manifolds with boundaries, and the boundaries will be the links. So if before the link degenerated to a point, and this was common to all singularities, by resolving we created now a morphology, and different singularities have links which degenerate on different objects, and this difference can be now reflected in the internal structure of the link. So how to get to this link? Well, the problem is that we have many choices. We are interested in the link of one object, the germ seen abstractly, but to get at this description, we need first to embed it somewhere in a smooth space, and then to choose coordinates in that smooth space. And then to choose sufficiently small levels. A lot of choices. The problem is how to show that all these choices lead to the same object, and how to arrive at a definition of this common object. So Mumford begins to describe in which ways topologists approached the theoretical problem of definition of a tubular neighborhood. And he says that the person who was nearest to what is suitable in his context was René Thom. He did the following. For a suitably restricted class of positive C-infinity functions f, such that f of p is 0 if and only p is in K. So what does it mean? We are in a big, say, simplicial complex. K is a subcomplex. And René Thom says, look at a function which is C-infinity and which vanishes exactly on the subcomplex. And then look at levels f equal epsilon for epsilon sufficiently small. The catch is how to suitably restrict f. To suitably restrict it such that all the choices will lead to isomorphic tubular neighborhoods and boundaries of tubular neighborhoods. Here, the archetype for the inverse of f may be thought of as a potential distribution due to a uniform charge on K. Why? Because this potential explodes when you go to the portion where you have the charge. And here we don't want to get to infinity, we want to get to 0. That's why here appears this 1 over f. In our case, as we have no wish to find the topological ultimate, we shall merely formulate a convenient and convincingly broad class of such f, which includes the P2 of the introduction. And then he defines a class of admissible functions. This, I won't show you the definition because it won't serve anymore in my talk, but this can be an exercise for you. How would you define admissible functions? And I think there is no ultimate. The class of admissible functions depends on the problem you want to attack. And then his problem is, what we must now show is that there is a unique manifold M such that if f is any admissible function, M is homeomorphic to the small level sets of this function. So this is what he wants from this class of admissible functions, to give you a unique manifold. And then he describes a way to construct from the exceptional divisor this prototypical manifold and to prove that all the choices of admissible functions lead to the same manifold. And the image, which is the key of construction, is this one. And in the text, you see that he describes this picture using the word plumbing fixture. And since it was written here, it propagated, and then one speaks about, in fact, many plumbed objects. But just let me show you the relation between the text and the image. So you see here 1/4 in the text. You see here the point with coordinates 1/4, 1/4. Then you see here that you have two real coordinates, but these real coordinates are sums of squares, u square plus v square and x square plus y square, which appear here. This is a way, in fact, to describe a part of a four-dimensional space. And you see that inside this four-dimensional space, one considers a hypersurface described by this equation. And this is the pre-image of this arc of generalized hyperbola here inside. And the plumbing fixture is something which allows to glue what happens on two different components of the exceptional divisor. One which corresponds to this horizontal line, the other corresponding to the vertical one. And these parts, one arrives here, and there is this common part here, and the gluing is produced there. That gluing is called plumbing. So at the end of the story, the manifold which he constructs is endowed with a projection, a surjective map, to the exceptional divisor. It is the map phi here in the text. Using this map, we can decompose M into elementary pieces, taking just the pre-images of the irreducible components of the exceptional divisor. Or you can decompose differently by taking some unions of components. You can go to the market and say, I want to buy this, this, and this. And then you take the pre-image of that union. And you get a lot of sub-pieces which come from the exceptional divisor. Now, if one wants to begin to understand M using this projection, it's important to understand also the fibers. And this map has fibers which are very simple. In fact, above a smooth point of the exceptional divisor, one has a circle. And above a singular point, which we know to be a normal crossings point, one has a two-dimensional torus. So those tori in a three-manifold decompose locally as a three-manifold. And we have circles which come from both sides. But in fact, they don't glue. There are different circles, even homologically. And on the torus, their intersection number is 1. And this kind of decomposition of three-manifold was called afterwards, with this prototype, a plumbing decomposition of the three-manifold. But be aware that the word plumbing applies both to the tubular neighborhood and to its boundary. So you will find plumbed four manifolds and also plumbed three manifolds, the prototype being here. These are among the first representations of such plumbed manifolds, coming from the book of Hirzebruch, Neumann Co., Differentiable Manifolds and Quadratic Forms. and from the wonderful book of Briscorn and Knurrer, Plane Algebraic Curves. Wonderful because in it you find, I think, hundreds of pictures, like the one on the right. So you see that the place where plumbing appears is represented here. This you can interpret as a region of conflict between the fibration. You have a normal fibration to one curve EI, the normal fibration to the other curve EJ, and here they are in conflict. And to understand what happens there, you see a prototype of a region which is a Cartesian product. Here the Cartesian product is very simple, it's simply a product of disks. And you see, when you do this plumbing, which you can do concretely in space with sheets of paper, you can build this object in three-dimensional space, you see that you construct corners on your surface. And if you think about the locus of corners, here there are 4 points. This set of 4 points is a Cartesian product of the set of 2 points, the extremities of this segment, and 2 points, the extremities of the second segment here. So if you think that this is an analogy and what you want to understand is the complex situation, there you have 2 disks. The boundary of a disk is a circle. So there you have 2 circles, and the Cartesian product of those 2 circles is a 2-dimensional tori. So those 2-dimensional tori are exactly the corner loci. So many geometers say they don't like corners, but if you allow them, you see exactly the objects you need to understand the topology. So in fact, here it's like for singularity theory. When I discuss with colleagues who are smooth geometers, they say that they are afraid of singularities. I think here we know that singularities are a source of gorgeous morphologies. So here it's another lesson. Corners are very useful. So now that you saw these prototypical decompositions of links, let me tell you about the Milnor fibers and their way to decompose them in an analogous way. So here are 2 drawings which come from Milnor's foundational book. You see that they are similar. In both of them, we have a representation of a sphere. S epsilon here is a sphere of radius epsilon around the origin of Cn. And here we have, in fact, the f-1 of 0, which has a singularity at the origin. The part inside the sphere is represented dashed here. And then one perturbs this a little by taking f-1 of C, with C a small perturbation of 0. Then what gets, again represented dashed, is something which does not have any more singularities. And this is a Milnor fiber. But you see that in these pictures, the Milnor fiber is not represented alone. You see also a representation of a vector field which pushes it inside the sphere. And this is called F index theta. And this is again a Milnor fiber. And they are called Milnor fibers because they are fibers of a fibration. And in fact, there are 2 fibrations. One which is called the fibration in the tube, and here you see a representation of various fibers in the tube T. And again, you see here trajectories of vector fields which pushes this in the sphere. And here you see the sphere S epsilon to the power m-1. In fact, this second picture comes from the end of the book when Milnor asked questions about his extension of the theory on the complex domain to the real domain. So that's why here you have simply m-1 and not an odd number, because here we are in a context of maps from Rm to Rp. So what are these 2 fibrations? The starting point is a holomorphic function, and in Milnor book, in fact, it was a polynomial. But let's say holomorphic because the theory then was extended to this realm. The main hypothesis here is that we have an isolated critical point at the origin. And then one can define a Milnor fibration in the tube T, which is shown here. and in fact over the boundary. So that's why you could say that here the boundary is composed of two parts. This one represented here, and in fact the extremities, two caps here. But if you imagine that you are in an open ball, the only boundary is the one which is fibered here. So please interpret the boundary of T as the part inside the open ball. And this, if you restrict F to this, well, the tube is a pre-image of a small circle around the origin in the target of the function f. And the second Milnor fibration is, instead of looking at f restricted to the sphere, we look at the argument of f, or better still, the quotient of f by its absolute value, which is again a map towards a circle. And it turns out that both fibrations are isomorphic. And the way Milnor had to prove this isomorphism was using a vector field by pushing one into the other. So that's why you see those trajectories of vector fields. And the closures of those fibers, because I told you that here I was looking in the open sphere, and here in the sphere, in the open ball, and here in the sphere, we are working in the sphere outside the locus where f vanishes. In order to have this quotient well defined, we have to take a closure of such a fiber, and we get compact manifolds with boundary. This is part of the theorem proved by Milnor. All those are representatives of Milnor fibers. And you see that again there are many choices here, and appears a basic problem why all of them lead to the same object. But it's true that they lead to the same object. So what was Milnor's motivation? Well, one learns this from a paper I love. It's one of my preferred papers on singularity theory, Recollections of Briscorn, published in 2000. Singularities in the work of Friedrich Hirzebruch. In this paper, he speaks a lot about himself. And one could say, well, he puts Hirzebruch in the title, but he speaks about himself. But it's not true, because he explains that his obsessions come from Hirzebruch, who was his PhD advisor. And even in postdoc, he asks to Hirzebruch, what should I do now? And the direction where to look was indicated to him by Hirzebruch, who came with very important impetus at the crucial moments. And here we see the beginning of a letter from John Milnor to John Nash from 1966. 1 week before the letter, John Nash met Milnor, they were friends, and Nash was discussed before with Briscorn, who explained him what he was doing. And then Nash explained to Milnor what Briscorn was doing. And Milnor said, "Dear John Nash, I enjoyed talking to you last week. The Briscorn example is fascinating. After staring at it a while, I think I know which manifolds of this type are spheres. But the statement is complicated and the proof doesn't exist yet. Let sigma of P1, Pn be the locus. First equation, a sum of powers of the variables equals 0. Second equation, which defines a sphere. The first equation defines what are called as Pham-Briscorn singularities. And if you want to see why Pham, you have careful explanations in this paper. I tell you about Pham-Briscorn singularities because they will occur again in my mini course. And in the same letter, there is a drawing, which is this one. And Briscorn explains that at the moment when he saw this, because Nash showed him the letter, he understood nothing about the drawing. But now, with hindsight, we can see here the germ of Milnor's book. So you see the Milnor tube. And also, why Milnor was fascinated? Because 10 years before, he had published a paper when he showed that exotic spheres existed. And this, in fact, was a marvel for all topologists in the world. So the examples of Briscorn showed that one can describe those exotic spheres, which Milnor had described by cut and paste approaches using quaternions, using algebraic equations. So you see, not everybody can be fascinated with anything. You have to be prepared. So this is how I imagine how Milnor was prepared to be fascinated by this. But you see also fascination depends on a context. And that's why for me, when I prepare a talk, it's very important to try to embed the audience in a context which allows them to get part of the fascination. And this is an art, so I don't know if I succeed in giving you this, but this is what I try to do by following this order without giving you precise definitions. I think one can understand the definition only if sufficiently fascinated. So let's advance. If you want to see how this germ developed and fascinated tens of people, you can read a recent paper by José Seade, published in 2018, on Milnor's vibration theorem and its offspring after 50 years, which he dedicates to Milnor, to Jack, whose profoundness and clarity of vision seep into our appreciation of the beauty and depth of mathematics. So you have a lot to read also here. You see, you have more than 60 pages. So I promised you to explain how plumbing led also to decompositions of Milnor fibers. So here I show you two drawings coming again from the book by Briscorn and Knurr. They are similar. You see the different segments represent symbolically a portion of an exceptional divisor. Here, in fact, for a sequence of blow-ups of the origin of C2. But you can imagine that this comes from a resolution of a surface singularity. And symbolically, this curve here is a boundary of a tubular neighborhood. Strictly speaking, it should not go like this, because here you don't have place to continue. These components should be closed manifolds. So you see, the symbolism has limits. But it's enough to see what we want to do. And now we are looking at a resolution, but which is not only a resolution of the singularity. It has also the property that if we look at a bigger divisor, the exceptional divisor, which is a total transform of f equals 0, it is still a normal crossings divisor. So that's why you see here you have dashed components. Those are transforms, strict transforms of f equals 0. And here we are interested in a tubular neighborhood of this bigger divisor. And inside this tubular neighborhood, we can look at the fibers of f, which are represented symbolically here as these smooth curves which go along the exceptional divisor. Because we get a decomposition is the same way as before. We can restrict now the projection from the tubular neighborhood to the exceptional divisor. We can restrict it to the Milnor fibers. Why two representations here? Because this is a second representation which allows to concentrate on the plumbing fixtures. Also there, one has to analyze carefully what happens, and this is a way to tell you, just pay attention to those places. And to these two representations, they associate two representations of the Milnor fibers, this time intrinsically. I told you that here we are in C2, so those Milnor fibers are in fact surfaces, and what they get as decompositions of the surfaces are shown here. The parts inside the plumbing fixtures are these parts here. These parts here of junction are crucial when we want to understand the geometric monodromy. Because in fact, some power of the monodromy becomes a product of den twists concentrated there. And so that's why, in fact, if you look on the left and you glue directly the cylinder, say this cylinder here, to this part, you get only a circle. And you don't have the place were to think about powers of Dehn twists here. Here you have the place to draw spirals. So they are needed if you really want to see what's the action of the geometric monodromy. Now that we saw these two kinds of decompositions, let us think about something which can be annoying for some kinds of mathematicians. For instance, Grothendieck. Here is an extract of, I think, his text, which is most widely understandable. The majority of Grothendieck's texts necessitate, in order to be understood a little, to make a PhD in that domain. If you want to explain them to, for instance, somebody doing probabilities, undoable, I think. But this text is absolutely fantastic because I think it's readable by any mathematician. It is called Esquisse d'un programme, and you can, if you don't understand French, you can have access on internet also to its English translation, Sketch of a Program. And here it's a place where he complains about something which is present in everything I showed you. This naive vision immediately encounters various difficulties. The first is a somewhat vague nature of the very notion of tubular neighborhood. Those emphasized parts of text are mine, not in his text. I want you to see the main points of my discussion, which acquires a tolerably precise meaning only in the presence of structures which are much more rigid than the mere topological structure, such as piecewise linear or Riemannian, or more generally space with a distant function structure. The trouble here is that in the examples which naturally come to mind, perhaps those I showed you naturally come to your mind now, one does not have such structures at one's disposal. At the best, an equivalence class of such structures, which makes it possible to rigidify the situation somewhat. So here you have a general problem of defining objects when you have to make choices. And Grothendieck's vision of mathematics made him find this very annoying. And I think it's important to understand these kind of things. We think that mathematics is only about logic. No, it's also about what we find annoying. And it would be very interesting to have a kind of preliminary list of what different mathematicians found annoying and made them build theories in order to make something less annoying. So here what we had, you saw, we had a lot of choices of embeddings and of admissible functions, a lot of choices before getting to the link or to the Milnor fiber. So I want to present you something which is more canonical. And the prototype of this was something which was very basic to Riemann. Let's read Riemann, a very short extract from his first paper, his thesis, Grundlagen für eine allgemeine Theorie der Funktionen einer veränderlichen komplexen Größe, 1851. The study of the connectivity of a surface is based on its decomposition via transverse cuts, that is, lines which cut through the interior from one boundary point simply, no point occurring multiply, to another boundary point. I have no idea if Riemann really cut paper in this way. I imagine so. But in any case, this operation for him was intuitive. He did not feel the need to describe it in another way. It was obvious that one can do this. And if you read this, what is obvious is that it is canonical. In his description, there are no choices. So if we try to imagine how nowadays with our foundations of mathematics we can describe such a canonical operation, it's not too difficult. A way would be to perform this locally. Take a point on your curve, take a small tubular neighborhood in which you see, in fact, a disk, and the curve cuts it into two half disks. So You take the complement of the curve in such an open disk. It has two connected components. Take each one of them, take the closure in the surface, and all those closed pieces, re-glue them with the same gluings as before. So if you do this, you add two boundaries where you see we saw only one. So it is doable, you see, with what we learned as basic topology. But now my question is how to cut along higher codimensional submanifolds. A higher codimensional submanifold locally won't disconnect. So we cannot do the same trick. We need something different in order to cut. For instance, what interests us, along a divisor with normal crossings in a complex manifold. Well, it turns out that such an operation was introduced by Acampo in his paper La fonction zeta d'une monodromie in 1975. And here is a paragraph where he describes this. He starts in any dimension from a complex manifold X, and inside it, a simple normal crossing divisor, whose components he called Cj. And he said that for each such component, he looked at the map Pj, which is the real-oriented blow-up with center Cj. If you read the first sentence, you say, I should go somewhere to see the definition. No, the definition was the next sentence. Therefore, above X, a point of Cj, lies the real-oriented normal directions to Cj at X. And Pj is a diffeomorphism outside Cj. So outside Cj, we do nothing, like in a usual blow-up. And Cj is replaced. Each point of Cj is replaced by the real-oriented normal directions at that point. And that is a circle. Thus, Zj becomes a differentiable manifold with boundary, and its boundary is diffeomorphic to the boundary of a tubular neighborhood of Cj in X. So you see what we have here is a description of a canonical operation which builds the result of removing the interior of a tubular neighborhood. But it achieves this without removing the interior of a tubular neighborhood. So if we are interested in the complement of a tubular neighborhood, well, we get it without choosing a tubular neighborhood. So this part of non-canonicity is eliminated. But now we have many components. How to remove the interior of a tubular neighborhood of the whole divisor? Well, by the operation of fiber product of the various maps Pj. Then Z will be a differentiable manifold with corners, and pi is a diffeomorphism outside X0. The last thing is that the manifold M, which is the boundary of this operation, is homeomorphic to the boundary of every regular neighborhood of X0 in X, and rho is a retraction. So X0 here is the union of the Cj. So let's see this in a drawing. First of all, my first drawing is the simplest situation. We have a complex curve, and we have a point of it. It's the simplest normal crossing divisor. What means to replace it by all the real-oriented directions there? Well, it is this map here on the left. We replace the red point by this circle. So you see that one real-oriented direction is this one. Another one is represented by this oriented ray. Now, when you tend to the origin along them, you arrive at different points. And because in this situation here to the left, you are on a different real-oriented direction, you get two limit points here. The usual blow-up is represented here on the right. Here, the whole line arrives at the origin at the same point of the red circle. So in fact, this surface here, which on the reals is a Möbius band, is obtainable from the left by simply identifying the antipodal points on the circle. So if you do this antipodal gluing, you get this one. So this is this horizontal map. So you see the operation of Ocampo performs this at each smooth point of the exceptional divisor. And when you have different components meeting, there you have different circles, and when you do those fibered products, punctually you have Cartesian products, and you get Cartesian products of circles, and you had tori of various dimensions. If only two components meet, you have a two-dimensional torus. If you have three components, a three-dimensional torus, etc. So let's do the analog of this now in Riemann's situation, but let's allow a crossing of the curve on which we want to cut. So if we do this and you look at a point, say here, you have two real normal directions. So when you cut here, you see that you build two copies of the red curve, and the same along the blue curve. But where they meet, you see that you have these 4 points, which on the complex side, as I explained before, represent a two-dimensional torus. So you get a canonical way of building a representative of the complement of the interior of tubular neighborhood without choosing a tubular neighborhood. And you see that we are in the same philosophical realm as that which made Riemann feel that one has there a canonical cutting operation. Now, log structures are something which allows to do the same. So you say, why do the same? Well, there are situations where it's not needed to go there. Ocampo's definition is perfectly suited. In particular, if you work only with simple normal crossings divisors, you can work with Ocampo's definition. So why bother about something which looks more complicated? Well, this generalized real-oriented blow-up, which is allowed by the notion of log structure, which is called rounding, first of all, is functorial. So being functorial, when you want to do many constructions, you do not need at each moment to think geometrically about what you are doing. You simply write maps and you apply functoriality. And it allows you to get constructions which are very easy to read like a kind of computation or an algebra. Second, rounding produces a desired topology. It means the same as removing a tubular neighborhood for more general divisors than those with simple normal crossings. I told you before toroidal. Well, for toroidal boundaries. Rounding may also be avoided when one wants to prove homeomorphisms of boundaries of tubular neighborhoods. Remember that in the Milnor fiber conjecture, we had different Milnor fibers, and part of the conjecture said that a part of a Milnor fiber can be encountered inside another Milnor fiber. So we don't need to go and to think in terms of Milnor fibers. Once we understand that those parts come from rounding applied to some log space, it's enough to prove isomorphism of log spaces. And log spaces being spaces structured using sheaves, one can use the general theorems which allow to prove isomorphisms of sheaves. And in fact, this is extremely practical because one gets in geometrical situations concrete maps from one sheaf to the other. And for those concrete maps, one has the usual tools of sheaf theory to show isomorphisms. So basically, the basic proposition about the use of log geometry for understanding links or Milnor fibers is that if you have a divisor with normal crossings in a complex manifold, first, it induces a canonical log structure on M, so something, and that something can be rounded. And that rounding is homeomorphic to the real-oriented blow-up of M along D, whenever D has simple normal crossings. So this is a basic thing, and then at the end of my mini course, I hope to convince you that This works also much more generally, and it is very good for us that it works much more general. So now I promised to start from an overview of log structures, that part which is useful for these topological problems. So I will finish my first mini course with this. A log structure on the topological space is a special type of morphism of sheaves. Okay, no need for more precision. We will see the precise definition later on. For the moment, we look at the theory more globally, focusing on several properties. First property, terminology. A log space is simply a complex space endowed with a log structure. And now there exists a notion of morphism between log spaces. It is something which is in particular a morphism between the underlying complex spaces, but it is more at the level of sheaves. Now, the main example for us is that if we have a reduced divisor in a complex variety, no need to have smoothness at any level or normal crossings, then there is an induced structure of divisorial log space on the ambient variety. A divisor induces a canonical log structure. Now, if we have a morphism between two varieties and a divisor in each one of them, each divisor induces a log structure, which I represent for simplicity by a dagger as an exponent of the letter. In which sense, in which condition f induces also a log morphism. Simply if we have this operation, this condition here, that the preimage of the divisor in the target is contained in the divisor in the source. So you have to say, I take the preimage, but I can add things to that preimage. And that is very convenient for topology to do this. So you see here an example of setting which induces canonical log morphisms. A second kind of log morphism is obtained by pullback. If you have a map, like before, from V to W, and some log structure on the target, you can simply pull it back on the source. These kinds of log morphisms will be called strict in the sequel. So strict, this is a terminology in this field, and they have special properties. We will see shortly one. Now comes rounding. Each time you have a morphism of log spaces, you can round the morphism. The symbol I imagined last year, because you have other symbols in the literature, in general it is called log, and to call the operation of rounding log when already you have a log space for me was very annoying. And in fact, in the situation, the prototypical situation, when you round the divisorial log structure, which is defined by the center of a disk, it replaces that point by a circle. I wanted to recall that the point is replaced by a circle. So for the moment, I am very happy with this. A symbol which shows that the point is blown up in the circle. So simply, phi is rounded in that way. So that rounded map is a map of topological spaces. But second, remember that you have a log structure is some sheaf on some topological space. The underlying topological space is denoted simply between absolute values. And if you say that rounding is a kind of cutting, we said that cut, in the spirit of Riemann, projects to the starting topological space. So this is the map. So this is a result of cutting W as prescribed by the log structure. And now if you have a complex manifold endowed with a log structure induced by a simple normal crossings divisor, this last map is homeomorphic to the real-oriented blow-up morphism of the manifold along the divisor. But even if the normal crossings divisor is not simple, you have the same thing. So you see, in Ocampo's construction, it was important to have a simple normal crossings. Here you see a first advantage of logarithmic structures, that you need only to care about local properties. And this is a basic fact of sheaf theory. Every time you define something in terms of sheaves, everything is completely local, and you do not need to add hypotheses as simplicity which are global. And finally, well, we saw that you can round the morphism of log spaces, and each one comes with its rounding projection. All these sit in a nice commutative diagram. This diagram is commutative. And some commutative diagrams are better than others. The Cartesian diagrams or the pullback diagrams. It turns out that when you have a strict morphism, well, this will be a Cartesian diagram. So in particular, when you restrict a divisorial log structure to the divisor which gave it birth, you have this property to have a Cartesian diagram which allows to understand the topology. And this is finally how it is used in this context. If you start with a strict normal crossings, simple normal crossings divisor in a complex manifold, this is this map. Here we are in the analytic category. Just look at the corresponding log map. It means W dagger is W endowed with a divisorial log structure induced by D. Now restrict it to D. You get a log map which is strict. Here we are in the log category. And now round everything, and you get this diagram which is a Cartesian square. Being a Cartesian square means that here what we want to understand, this part of the real-oriented blow-up which projects to D is simply restricting the real-oriented blow-up to D. Therefore, the boundary of the tubular neighborhoods of D in W is encoded by this log space. And I am finishing with this today. D creates on the ambient space a log structure, which you can restrict to D, that encodes the topology of the boundaries. So then you can work with those things without looking in any way to the boundary. You work only with that D dagger. And that, I hope, gives you a small desire of knowing better what all of this means. Thank you very much for your attention.
So, are there any very short questions?
So at some point you said that you weren't assuming anything on the divisor, so to get the log structure you need the divisor to be normal crossings?
No.
No. So the question then is, if the divisor is not normal crossings and you consider this log structure, then you don't have like this topology of a tubular neighborhood.
You get more complicated topologies, but you have also the topology of complements of neighborhoods each time you look at divisors which are toroidal boundaries. So if you look at the toroidal variety and its boundary, then it's okay. And I will explain this in a later talk.
So the question is then, if is what gives the Milnor fiber is the topology of the boundary of a tubular neighborhood, or this more complicated thing?
The topology of the boundary of the tubular neighborhood will give the total space of a Milnor fibration. And in fact, the Milnor fibration will be given by rounding not only one log space, but a morphism of log spaces. And I will explain you this tomorrow. I will start tomorrow with a way to apply this, but not to an individual pair of a divisor in W. We have to start from F.
Thank you.
Sorry, just a small comment on the question. Generally, I think the theorem you pointed with the tubular neighborhood works under some more general situation, in Kato Nakayama's paper, they have this condition that the log structure needs to be so-called relatively coherent, and that's a sufficient condition to ensure the rounding.
Yeah.
I wrote in my Kato Nakayama paper how it can be generalized even further. But in the original work of Kato Nakayama, the correct condition is you need to have a relatively coherent log structure. It's more general than toroidal.
Yeah, thank you. I wanted to avoid these terminologies just to give the initial ideas. So I want to give the most general version, because my experience was that when one does not know anything, to present relative coherence is difficult.
Okay, so we can thank again Patrick for his talk.